So this is a lecture 12 on Artinian and Noetherian module. So we discuss on Artinian module separately and Noetherian module separately. Now we discuss together. The Artinian and Noetherian module, there are some results on that. Actually, it's a counter result, counter example. Rather. So an Artinian model need not be finitely generated. So an Artinian model may not be finitely generated number. Obviously, any finitely generated module is Artinian, but Artinian model may not be finitely generated. Converse is not true. Finitely generated model need not be Noetherian. So Noetherian model is finitely generated, but finitely generated may not be Noetherian. So again, this is converse is not true. We'll see in this example later. Maximal submodel does not exist in Artinian model. Whether maximum submodel exists in Noetherian model, but may not exist in Artinian model. May exist if both the submodel is both Artinian and Noetherian both, then it exists. Minimal submodel did not exist in Noetherian model. So minimal submodel is exist in Artinian, but may not be in Noetherian. And Artinian model need not be Noetherian. So Artinian model may not be Noetherian, and Noetherian model may not be Artinian. So there are models which are not either neither Artinian nor Noetherian. So there are 4 cases possible. So both Artinian and Noetherian is obvious. Any vector space, say R over R, one-dimensional vector space R over R. The field is R and the vector space is R. That is just a one-dimensional, finitely generated. There is only two subspace. They are also finitely generated. So these are Artinian and Noetherian both. Now there are some model which is not Noetherian, not Artinian. There are a model which is Noetherian but not Artinian. There are model which is Artinian but not Noetherian. We will see in the one by one. There are 7 things, so we will see this. Before that, we discuss on the group of p-nth roots of unity. What is nth root of what is nth root of unity? So it is a solution of all x to the power n equal to 1. All the solutions. What are the solutions? We know it is cos 2k pi by n plus I sin 2k pi by n. So these are the solutions of all to x to the power n k equal to 0 up to n minus 1. These are the solution, and we know this forms a cyclic group. This forms a cyclic group. Now we take that p to the power n there. If we replace n by p to the power n, where p is a prime number, p to the power n. So this is p to the power n, and this is goes to 0 up to p to the power n minus 1. So this forms a cyclic group. So we write that group as mu p to the power n. This cyclic group all p to the power nth root of unit for fixed prime and fixed natural number n. So we fix p and n. Say we fix p equal to 2 and n equal to 2. So x square. So it is just the roots of the x square equal to 1 is 1, minus 1, I and minus I. If you take p equal to say 2 and n equal to 1, then it is just x square equal to 1 and minus 1. If you take p equal to 2, n equal to is equal to say 3, so it is x to the power 8 equal to 1. What are the roots? Roots are 1 minus 1 I minus I, and the other roots are 1 plus I by root 2, 1 minus I by root 2, minus 1 minus I by root 2, and minus 1 plus I by root 2. These are the all 8 roots of unity. If you take p equal to 3 and n equal to 1, the roots of x cube equal to 1 is omega square and 1. These 3 roots. If you take say this p equal to 3 and n equal to 2, then it is x to the power 9. What are the roots? The roots are that 9th x to the power 9 equal to 1. That means cos 40 degree plus I sin 40 degree, cos 80 degree plus I sin 80 degree, so on and so forth. So it's 360 by 9. So obviously for a fixed p, this is true. This is true because x square equal to 1, the roots of x square equal to 1 is actually belongs to the root of x to the power 4 equal to 1, which are the roots of x to the power 8 equal to 1. It's contained in this root, which are x to the power 16 equal to 1. So it's contained. The roots of the lower is contain the higher degree, higher power. So that's why it's a subgroup actually. Now consider this thing, this union over all this. So p equal to 2. consider P equal to 2 for example, then if P equal to 2, then the first mu P is just singleton one element. Then P square has, that means, so sorry, 1 and minus 1. Then P square 4, so it is 1 minus 1 already there, so it is I and minus I. Then P to the power 3, that means 8, then it is 1 by root 2, 1 minus root 2, 1 minus I, minus 1 plus I root by root 2, and minus 1 minus I by root 2. Then P equal to 2, N equal to 4, so 16. So again, this 16, that means cos 22.5 degree plus I sin 22.5 degree, so on and so forth. So this collection forms a group, but this is not cyclic. This again a group. This is a non-cyclic group. This is infinite. Obviously, it is infinite, and this is abelian. But it is abelian because it's a complex number. So it's a subset of complex numbers, so it is abelian. So it is a subgroup of complex numbers. So it is an abelian group, infinite and non-cyclic. Easily you can prove that it is non-cyclic. Because if it is cyclic, if it is generated by something, then it is a root of say P to the power 5, then that cannot be generated the all roots of P to the power 6. So that's a non-cyclic. Now, every proper subgroup is finite. Not every proper subgroup is finite. That is the interesting. The every proper subgroup of this is and just equal to sum for some n P to the mu P to the power n. So if you take any subgroup, proper subgroup, other than the itself, it will just some P to the power mu P to the power n. These are the all subgroups. So 1 minus 1 is a one subgroup. 1 minus 1 I minus I is another subgroup. So these are the all subgroups other than that itself. And obviously this is not finitely generated. And every finitely generated subgroup is proper, and every finitely generated subgroup is proper, and hence group is finite. Every finitely generated group is itself finite subgroup. By the way, that group is a module over Z, and subgroup is a submodule. Remember, once I write subgroup, that is also submodule. Now, mu P star is not a finitely generated. It can't be finitely generated because all finitely generated subgroup are proper and finite, but itself is infinite, so it can be finitely generated. Now, mu P is an Artinian module, which is not finitely generated. So it is an Artinian module. So this is the condition hold. Because this is the condition hold. Why is this condition hold? Because if you take that mu P star, then if you take the something, then these are finitely proper. So these are finitely generated. So that it must be stopped somewhere. It must be equal. It can't be less because the first one may be infinite, but next one, the other, these are all finite submodule. These are all finite things. So it must be equal after some stage. So this is a condition hold, but it is not finitely generated. So this is a example of counter example. The finitely generated may not be finitely generated. Artinian may not be finitely generated. But this is not Noetherian. And maximum submodule does not exist. Why it is not Noetherian? That is not because we start from ascending chain condition doesn't hold. So we start from this. Actually, this is the example. This is the SCC condition hold, but it's not stationary. It's proper. So this is the SCC condition hold here. It does not hold here. So it's ascending chain, but not stationary. So SCC condition does not hold. That's why this is not Noetherian. And hence maximum submodule does not exist. It is a maximum submodule does not exist. So these are the result. So what we prove? We prove three things here. That Artinian module which may not be finitely generated. So Artinian module which is may not be finitely generated. This one we proved by a counter example. Then Noetherian module. Noetherian module may not have maximum submodule. So it is Artinian but not Noetherian. So it is Artinian but not Noetherian. This also true, and maximum submodule may not exist in Artinian. So it is Artinian and maximum submodule does not exist, and is also not Noetherian. So these three we proved here by this counter example. Rest for we give another example. Finitely generated module need not be Noetherian. So we have to we will next show the finitely generated module which need not be Noetherian. That example, finitely generated module need not be Noetherian. So we have to give an example of finitely generated module. We have to give an example of now we already put the three things. So next we prove there is a finitely generated model need not be Noetherian. So take that ring, which the coefficient from Z, and the variables are x1, x2, xn dot dot. There are infinitely many variables. But remember that polynomial has finitely many terms. The number of variables may be infinite, but polynomial, for a particular polynomial, each polynomial has finitely many variables because there are finitely many terms. So what are the terms? The terms may be like a1, x1, a1, a2, a3. These are all the coefficients are Z, integer. Some a1 any power 100 or x2 to the power 700, like that, and maybe x1 into x2 to the power 5, x3 to the power 9, that also there. So you have to take all these variables and you can take the product and sum. That you can do, no division. X1 by x2 is not the polynomial. So these are the polynomial of more than one variable, and this is a ring. We know this is a ring, and that ring is finitely generated over itself, because every ring is a module over itself, and it is finitely generated because it is generated by one. So it is finitely generated module, but this is not Noetherian. Why? Why this is not Noetherian? There is a mistake here. So it is not x2 generated by x2, it is generated by x1, x2. So the polynomial ring generated by x on the that submodule, and the ideal is also ideal of that ring. So the ideals are actually submodule. So that ideal is a sub-ideal of that, and that there is an ascending submodule or sub-ideal, but this means it is not stationary. So it is not, SCC doesn't hold. That's why it is not Noetherian. So we have this example that Artinian module may not be Noetherian. Next we show that the race 3 for now Z. For Z is Noetherian but not Artinian. Z is Noetherian but not Artinian, and it has no minimal sub. Why? Z, we can have this descending chain, and which is not stationary. But every ascending chain is stationary, because we know if nz is subset of mz, then m must divide z. So you can start with any number, but if you take the ascending chain, you must stop. But if you descending chain, there is no stop, may not be stop. So DCC doesn't hold, but SCC. That's a Noetherian but not Artinian, and is a no minimal submodule. The rest, the last one, you have to show that there is a module which is not Noetherian, not Artinian. So direct sum of any finitely many vector non-zero module or infinite dimensional vector space. So any infinite dimensional vector space or direct sum of infinitely many non-zero module is neither Noetherian nor Artinian. Why? So take a vector space with basis is say this one, V1, V2. These are the basis, infinitely generated vector space. Now we have always, there is a DCC chain which is not stationary and SCC chain which is not stationary. How? Now this is a SCC chain. So subspace generated by V1, then subspace spanned by V1, V2, then subspace spanned by V1, V2, V3. So this is SCC. Sorry, this is the ascending chain, but this is not necessary. So SCC doesn't hold. And similarly, you take V, then it is a superset of span of V2, V3 dot 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 dot. Then is a proper submodule which is spanned by V3. We just dropping one more. So this is a descending chain which is not stationary. So it is not Artinian, not Noetherian. So this gives all the counter example, and this completes the thing of Artinian Noetherian model. The only thing we left is the exact sequence, short exact sequence, and we discuss in the next video in this short exact sequence and the exact sequence and the property.